We watched a video on Friday that illustrated for us a new principle, a new law called the law of conservation of momentum, which says in an isolated system, the total amount of momentum will remain the same. In other words, just like the law of conservation of anything else, blank cannot be created or destroyed. Momentum, in this case, cannot be created or destroyed. In an isolated system, the total amount of momentum will remain the same. What do I mean by that isolated system term there? An isolated system is a system in which, yeah, there's no external forces. Good. We're isolating a system from external forces, and when we do that, the total amount of momentum will remain the same. Now, that doesn't mean that the momentum of individual objects will remain the same. Okay, when I'm running one way and somebody else is running the other way and we collide, my momentum will change. There'll be an impulse. I'll experience a gain or a loss of momentum, and so will the other person that I hit. When two cars collide, same deal. One of them gains momentum, one of them loses momentum. But the total amount of momentum, if we account for everything within the system, as long as it's isolated, will remain the same. And this is going to be useful whenever we're analyzing certain interactions between those 2 or 3 or 4 or 5, whatever objects. The first situation, the first interaction is a collision. And that's pretty self-explanatory, I think. When two objects collide, two cars collide, two rocks collide, two people collide, when two things hit each other, that's a collision. And if we analyze the entire system of both of those objects, we can use the law of conservation of momentum as long as we have no external forces acting. But the other situation we can use conservation of momentum is when we have an explosion. And an explosion doesn't necessarily mean literally an object blowing up into a million different pieces. It can mean figuratively an object exploding. Like, for instance, a gun. Fire a gun. The gun and the bullet were one object before you fired it. Afterwards, that one object has become two. It's split up. Stand on ice with a heavy object, a medicine ball, let's say. Throw it. The medicine ball goes that way, you go that way. One object, you and the medicine ball, became two. That's an explosion, figuratively. For purposes of analysis here, we consider that to be an explosion. When we have a collision or an explosion, we can use the law of conservation of momentum if we analyze the entire system and if the system is isolated. We could choose to analyze the momentum of the ball. If we did that, we'd have to use impulse because it changes. We could choose to analyze the momentum of the person throwing the ball. If we did, we'd have to use impulse because his or her momentum changes. But if we analyze the ball and the person, we use conservation of momentum because the total momentum is remaining constant. The problems that we're going to do today, we will analyze the system. Therefore, we will use conservation of momentum. And we will make sure that we have an isolated system. There's no external forces. Let's go back to the third paragraph for a second here. Look at those two terms, immediately before and immediately after. Why is that important? Just before they collide and just after they collide. Now's your hand up there? No? If there's a collision between two cars, just after the collision, maybe they're moving at 5 meters per second just after the collision. How fast do you think they're moving 10 seconds after the collision? They probably stopped, right? What stops it? Don't overanalyze this. What stops these two cars after the collision is taking place? Probably going to be, could be each other, but somebody said it. Friction. Probably going to be friction, right? Friction is an external force. If we analyze that collision immediately after the collision takes place, then we haven't given friction really a chance to act. Right? We're analyzing it before the external forces become a factor. In other words, we're making it an isolated system, a system where there's no external forces. Now, if we leave it for 5 seconds, 10 seconds after the collision takes place, we've lost our chance. We don't have an isolated system anymore. So, analyzing one object, impulse. Analyzing all of the objects in the system, conservation of momentum. All right, I'm going to derive an equation for you here now for the law of conservation of momentum. It comes from Newton's third law. You guys remember what Newton's third law was? Or is? It's a physics 20 thing. For every action, equal and opposite reaction. Remember, if you had me from physics 20, I told you I really don't like that way of saying Newton's third law because I think it leads to some misconceptions. It's correct, but it leads to some misconceptions. I prefer to say if object A applies a force on object B will apply an equal and opposite force on object A. It's the same thing, right? I just think that's a slightly better way of saying it. Bottom line is, Newton's third law says this. F12 is equal to negative F21. If object 1 applies a force on object 2 applies an equal and opposite force on object 1. Newton's third law. Impulse, remember, you derive from Newton's second law, from F equals ma. Conservation of momentum comes from Newton's third law. F12 is equal to negative F21. All right, let's do some substitutions here. F12 is the same as saying m times a. M2 times A2 equals negative M1 times A1. With me so far? You got to know Newton's third law is F is equal to negative F, and that F is equal to M times A. Let's do some more substitutions. Let's replace A with delta V over delta T. M2 times delta V over delta T, 2, equals negative M1 times delta V over delta T, 1. Good? It's not that hard so far, eh? Let's see who of you can give me the next step here. I want to simplify this a little bit. Anybody see a way that I can simplify this, Matt? I can't take mass out of both of them because it's two separate objects and they both have different mass, right? If it was the same mass, I could cancel them, right? But they're not. Time can. Okay, if I'm running towards somebody else and we collide, I'm object 1, Jesse, you're object 2, I'm object 1, we collide. If I collide with you for 4/10 of a second, then you're colliding with me for 4/10 of a second, right? So even though these have different names, T2 and T1, they're both going to be the same value, so they disappear. They cancel out. Now we can see that M2 delta V2 equals negative M1 delta V1. What does this say? This isn't the end, by the way. What does this say? The impulse experienced by object 2 is equal and opposite to the impulse experienced by object number 1. So I'm running towards Jesse. Jesse's running towards me. I gain 10 units of momentum. Jesse loses 10 units of momentum. My impulse is equal and opposite to his impulse, right? If I gain 10, he has to lose 10 because the total has to remain the same. All right, now I'm going to stretch this out a bit. And this is where it starts getting a little bit ugly. But like I said, you don't have to copy this down if you don't want. It's the end that's really important for this. M2 times delta V is VF minus VI. We're going to call it V2F minus V2I. Final minus initial, object 2, equals negative M1 times V1F minus V1I. With me there? Just replace delta V with VF minus VI, object 2 and object 1. Now I want to distribute the masses. So it becomes M2 times V2F minus M2 times V2I equals negative M1 times V1F. Tell me what I put here. Negative M1 times negative V1I. Positive M1 V1I. I'm just going to change the order around here so that it looks like this. M1 V1I plus M2 V2I equals M1 V1F plus m2 v2f. So all of this comes from saying F12 is equal to negative F21. Comes from Newton's third law. What are we really saying right here? What's m times v stand for? Momentum. Right? M delta v is impulse, mv is momentum. We're saying the momentum of object 1 plus the momentum of object 2. In other words, the total initial momentum of this system equals the momentum of object 1 and the momentum of object 2, the total final momentum. In other words, pi equals pf. Total initial momentum equals total final momentum. Object number 1 might gain or lose. Object number 2 might lose or gain. But the total momentum will remain the same. Pi equals pf. This is the important part right here. This is just how we got there, to show you that, in fact, it must be true, assuming Newton's third law is true. All right. The best way to illustrate this is to do an example. And we've got a few examples here today. The first one is on page 477. It says a wooden block is attached to a glider. It has a combined mass of 0.2 kilograms. What does that mean? A glider on a frictionless air track is, let me draw a picture of it actually. We're looking at a cross section of this air track, looking at it from the end. The air track is usually triangular like this, and there's holes in it. And those holes allow air to come out like this. You put this kind of reverse vacuum cleaner to pump air into this, like an air compressor to pump air into this. Air comes out, kind of like an air hockey table, except it's triangular like this. You have this glider that sits like this on the cushion of air. The glider can slide back and forth on this track without actually touching metal against metal, which means the friction is very, very low. So it allows you to do some pretty good physics experiments because there is almost no friction. Make sense? These are very, very expensive, and that's the reason we don't have any. Okay? I'd love to have 8 of them so that we could have 8 groups doing an experiment with these air tracks, but they cost over $1,000 each, so the odds of us getting 8 of them are pretty small. But that's what's going on here. Okay, you got a wooden block on top of the glider. The wooden block and the glider combined are 0.200 kilograms. Okay? The block and the glider are at rest on a frictionless track. The initial velocity is 0. A dart gun shoots a 0.012 kilogram dart into the block. Let's draw a picture the other way now from the side. Okay, here's the glider and the block at rest. And here's the dart that's being shot towards it. It has a mass of 0.012 kilograms and a velocity this way of 0. That's what we're trying to find, right? After this collision takes place, you got the glider, the block, and the dart going off together. They're going to have a mass of 0.212 kilograms, and they're going to have a velocity of 0.78 meters per second this way. You guys with me on that? This is probably the hardest question we've done so far. It is. Because the wording, right? Figuring out exactly what's going on with this. Figuring out what our givens are and so on. Now, remember, I could choose to analyze the dart and use impulse. I could choose to analyze the block and the glider and use impulse. Or I could choose to analyze the whole system and use conservation of momentum. That's what I'm going to do right now, is the whole system. Pi equals Pf. How many objects do we have before this collision takes place? Okay, how many objects do we have over here in black? Ethan? 2. Yeah, there's 2. So we're going to say M1 V1I equals plus M2 V2I equals two objects, momentum of object 1 plus the momentum of object 2 equals, how many we got afterwards? Sadie, how many objects do we have afterwards? 1. Right? We still have the same things, but they're all combined together now. We're going to say it's MVF. Some people like to call this MTVF, mass total. I just choose to call it M. We got enough subscripts here as it is. M1 is 0.012 kilograms. V1I is what we're looking for. M2 is 0.2 kilograms. That's V2I. Check what's V2I. It's the velocity of the block and the glider before the collision. Yeah. No. Sorry. No, we know what it is. We know what the velocity of the block is before the collision. We don't know what the dart is, right? V1I. The block is 0, right? Just cross that off. The mass of the block, 0.2 times 0 is 0. Still two objects, but one of them is at rest, has no momentum. Combined mass, we know that after the dart sticks in the block, combined mass is 0.212 kilograms. VF is 0.78. Look at this. Solve for V1I here. I'm going to say 0.212 times 0.78 divided by 0.012. And I've gotten 13.78. Round that to 2 digits, 14 meters per second. It's a bigger number than my final velocity, quite a bit bigger. Does that make sense why? If something that's light transfers its momentum to something that's heavy, what's going to happen? It's going to slow down, right? The object that's heavy is going to be moving slower. Sure. Most times, guys, we're not going to fire a dart into a block. Okay? But where could this maybe be used in a more realistic setting? Not by everybody. Okay? Most of you guys will probably never do a calculation like this in the real world. But there are places where this is very directly applicable. In fact, almost this exact calculation is used every single day nearby you. And depending upon what career you choose, you may use that. What is this almost identical to? Forget about the dart. Forget about the wooden block. This is, picture a car at rest. Picture another car coming towards it, hitting it. We measure the final velocity of the cars based on skid marks and so on. We calculate the velocity of car number 1. The velocity of the car that struck the stationary car. Who would do that kind of calculation? Yeah. Sure. Maybe an insurance company, right? Maybe a police officer who's investigating a car crash, right? It might be useful to know whose fault the accident was. And part of that is how fast was the guy going when he hit the person, right? You can calculate how fast he was going based on how fast he was going afterwards. And even though you can't observe how fast he was going afterwards, based on skid marks and coefficients of friction, you can actually determine that fairly easily, how fast he was moving after the collision. And then you can work backwards to find out how fast he or she was moving before the collision by a calculation like this. All right? Okay, I'm going to give you 2 questions that go along with this. Remember, as you're reading these, to keep straight what's going on. Draw a picture. Keep straight what's object number 1. Keep straight what's object number 2 and what's initial and what's final. Ask yourself, how many objects do I have? If there's 2 objects, then put a term in for both of them. If there's only 1 object, then put a term in for that one. There has to be an MV for every object that you have. Know if you've got 2 objects or 1 object or 3 objects for that matter. And write a term in for each of them. See what you can do here? Call me over if you're having trouble. All right, let's take a look at number 1. It says a student on a skateboard with a combined mass of 78.2 kilograms. This is the student and the skateboard. Let's draw that here, right now. There's a skateboard. Okay, here's a student. Big skateboard. Student skating on the skateboard. 78.2 kilograms. And that's going to be 1.6 meters per second. What do you want to call that, by the way? Student and skateboard. By the way, they don't separate. They stay together the whole time, right? It's like you and your clothes walking down the hallway. You're one object, right? This is not, we're not saying that the student and the skateboard are 2 separate objects. They're one object. And they remain one object, just like you and your clothes remain one object as you walk down the hallway, hopefully, right? What do you want to call it? M1? Object number 1? Okay, or call it number 1. What's this at 1.6 kilometers per second? Is that going to be V1 or V2? That's going to be V1. Object number 1, initial or final? This is V1 initial. This is how fast object number 1 is moving. That's the skateboard and the student. How fast object number 1 is moving before the collision or before the interaction takes place. Here's a backpack over here. The backpack has a mass of 6.4 kilograms. We're going to call that M2, object number 2. The backpack is not yet a part of the student/skateboard. So we're going to make it a separate object here. What's the velocity of object number 2? How fast is that backpack moving, Tyler? 0. What are you going to call that? V1 or V2? I'm going to call it V2. V1 is the student/skateboard, right? V2. V2I or V2F? V2I. So far, so good? This is before. Now, after the interaction, we got a skateboard and a student, but now that student has a backpack on. Looks more like a Ninja Turtle there, doesn't he? Than a student with a backpack. The mass of this is 84.2 kilograms. I'm going to call that just M. Some people might like to call it MT for mass total. But remember, after the interaction takes place, we've got one object. Student, skateboard, and backpack all combined into one. What's the velocity of this student, skateboard, backpack combination? We don't know. That's what we're trying to find. We'll call it VF. Not V1F, not V2F, just VF, because we have only one object. So far, so good? All right, let's go to set this up now. PI equals PF. And we're going to say M1 V1I plus M2 V2I. We have 2 terms there because we have 2 objects before the collision takes place, before the interaction takes place. Equals MVF. Why only one term? Why only one term here after the interaction takes place? Because there's one object. 2 objects, skateboard student and backpack, become one. Skateboard student, backpack. Sorry? Yeah, kind of. 2 become 1. All right, M1 is 78.2 kilograms. V1I is 1.6. M2 is 6.4. What's V2I? 0, so we can toss that out, right? M2 times 0 is 0. Combined mass is 84.2 times V2F. That's what we're looking for. Now it's pretty straightforward, right? These, multiply these, divide by 84.2, and we should get 1.5 meters per second. Tell me why the velocity went down. Tell me why the speed decreased when the guy picked up the backpack. Same momentum, sorry. Yeah, same momentum, more mass gives me less velocity with the same momentum. Is that okay? Yeah. Okay, keep working for a couple minutes on question number 2. It is, on the surface, seems a little bit harder because you're looking for a different variable, the mass. That's okay, set it up the same way. Count your objects. Know how many objects you have before and after. Set it up, and lo and behold, you're just going to mathematically solve for mass no harder than what we just did. Time to look at number 2. Look, we have 2 vehicles here. We've got a car. We've got a truck. Here's the car. Here's the truck. Okay, after the collision, they stick together. So the car and the truck become one. We've got a mass here of 1,050 kilograms. What do you want to call that? Maybe M1? We're going to say something has a velocity of 2.65 meters per second. What is that? Is that V1? Is that V2? It's a velocity, clearly. V1 or V2? The velocity of object 1 or the velocity, the car or the truck? The car was the only thing moving. The truck is at rest, right? It's V1. Is it V1I or is it V1F? It's the velocity of the car. Done? It's the velocity of the car before the collision. It's V1I. What else we got here? The stationary truck, V2I. The velocity of the second object, the truck, initial equals 0. VF, that's the combined car truck. Final is 0.78 after they collide and move off. So car is moving at 2.65. Truck is at rest. Car and truck move off together afterwards at 0.78. I want to find M2, right, the mass of the truck. So let's say PI equals PF. M1 V1I plus M2 V2I. Why did I show 2 terms there? 2 MVs? Because there's 2 objects. There's a car and a truck. What happens after they collide, though? They become one. They stick together. So it's going to be MVF. 2 terms because there's 2 objects. 1 term because there's 1 object. 1,050 times 2.65. This disappears, right? Because V2I is 0 equals M, we don't know what that is, times 0.78. Solve for M there. I think it works out to be 3,500 or so. 3,567. Okay. Now, what have we just found there? Guys, just take a step back from this, okay? You're not like, don't get this tunnel vision on this one variable. Like, think about this. What have we just found? What have we solved for, Maddie? Yeah. Listen, that term is the combined momentum of the car-truck combination. So that mass is the combined mass. That's not what we want, though, is it? That's how we're going to get it. Let's subtract the mass of the car from it. And the mass of the car was 1,050. So I think that gives me 2.5 times 10 to the 3 when I do that. Is that okay? Yeah? Does it feel like it's getting a little bit easier? Trust me, once you get the hang of this, it's really not that bad at all. You gotta see how many objects you have before and after. Put an MV for each of those objects. And then plug in your numbers. Do some math.